it's going to sound a little robotic if for just a few minutes when I actually get into this lecture, but I really want to cover 2 points first. So we got 14 people. The first point is importance of attending lectures. So, this happens every semester so tell your friends who aren't here, because right now I'm speaking to the choir, but these lectures, if you miss lectures, you will be lost. I guarantee it. And it's not my fault if you're lost. I try my best, and I am merely a resource, okay, to help you with your learning. But I really want to emphasize it's important to keep up with the lectures, even though I'm recording them, and I think maybe some people are thinking that they'll just go and watch the videos, but I actually know how many people are watching them because I post them on YouTube, so I can tell how many views, and it's not encouraging. I don't want you, please get the word out, or if anybody hears this, please don't miss lectures. And the other thing, I'm glad that you keep me posted on any personal things that are going on, so we can accommodate and help. With the coronavirus, again, I want to try to accommodate you as much as we can. If you have to quarantine yourself, you need to make sure that I know, and of course I respect privacy on that, but the lab instructor needs to know if you're quarantining for a while. If you do become sick, the policy the university has is that if someone becomes sick and they can't, you're not going to be able to attend labs. That probably end up with they're really saying incompletes. It may be a necessary thing in a class. I hate to say it, and I hope that nobody gets sick. And clearly, if you are sick, even if you're feeling okay, but if you've been tested positive, you will spread it to other people. So please, of course, be aware of that. And the second thing is on the exams. And I'm kind of now talking out of two sides of my mouth, because I'm trying to enable us to be able to be safe as much as possible, but I've really got no choice but to do the exams in person. And frankly, it's probably going to be better for you to take it in person than to try to do it. Well, if you can't do it, here's the alternatives, okay? We're going to I've already set up the exam dates, so they're hard, firm dates right now. I'll send out an email on the dates because I don't want to waste time trying to fumble around finding the file. And I'm going to revising the schedule for the class and post it, because we fell a little bit behind, and I've adjusted it, and I got to try to stay on track with that. But we would have scheduled rooms for our exams. It's large rooms in the EMS, and it will be possible to have, there are going to actually be chairs that are, it's set up so that people are spread apart. And I'm getting that set up. If someone does not feel comfortable with that situation, then what the alternative is that we will make an appointment at the USR building, which is a lot more isolated, but I can't do this with everybody. I'm talking about some special cases. like myself, okay, so I'm going to have to come and administer this, but I'm a very high risk person on this coronavirus because I have a lung problem. And that's why one reason why I talk so funny. Uh, but if there's someone that, let's say you've got an immune system problem or something like that, you just don't want to go into the EMS, I don't blame you, but we'll have to go to the USR, which is the University Service Research Building. That's where my lab is, and set up an appointment for me to give you the exam. And I have to write a new exam for every person who does that. So it won't be good if everybody, the fact that I'm doing that, I'm trying to be accommodating, and I don't want that to become a disaster. If somebody has an immune system problem, or someone in your family does, that would maybe be a case where USR is what we would do. So let's go on to the lecture now. And I'd like to welcome you to Electrical Engineering 362, Electromechanical Energy Conversion. And this is Module 2, Magnetic Circuits Analysis, Lecture 3. So a little bit of a review of what we talked about previously, just to summarize everything. So far, we've been talking about magnetic components as a simple magnetic circuit. And this is the first one that we introduce you to. And as we go along in this class, for this period, we're going to show some examples of different types of structures. But the main point here that to review is that we've introduced the concept of MMF, that was this F term here, which is equal to the ampere turns, the current time number of turns in the coil. And that is the Ni is the same as what we were calling I enclosed, which is now this together, that's Ampere's law. And then applying it to this circuit here where we have a single simple core with a coil. It would be H in the coil, magnetic field intensity in the coil, times this, the mean length of the magnetic path in that coil, which is in the middle of the core there, and going in the direction according to the right-hand rule. We can find the flux density from this expression here. We talked about mu as being associated with both the air and the material of the core. So mu equals the mu naught times the relative permeability associated with the core. We then have also talked about flux and its relationship to flux density. That's right here. And then we were able to progress everything to an expression for reluctance, which is shown right here. So basically, the progression that we've gone through here is we've said we solved Ampere's law. We plugged the let's see, if we want to find, we've got this expression right here, and so the H sub C, H in the core, is equal to the B in the core divided by the permeability of the core. And so if we know this, we're able to plug that into here. And then we also know that the BC is the flux over the core area, so we're able to plug that into there, and then we end up with the this F equals the flux in the core times the length of the core, mu AC. And this is how we ended up with the reluctance. And there is an analogous relationship here to an electrical circuit where F is analogous to a voltage. It's applied to this magnetic circuit. The flux is analogous to a current, and the reluctance is analogous to resistance. So we can then write the magnetic circuit here like this. Okay, so the next thing we did was we said let's put a gap into this core. If we do that, then by Ampere's law, we actually end up with the magnetic field intensity associated with the core. That's this magnetic field, and there's also a length. It's the same length that we had before. Here we called this was your LC, right? Now the LC in this case would be equal to, let's just say, the LC without the gap minus the G. Now sometimes this is the gap length. Sometimes we call this LG, sometimes we just call it G. And then we have the magnetic field intensity in the gap right here times the length of the gap. That's the physical length across the gap, G or LG. And now we can go through the same process of, we know that there is a flux density in the gap and there's a flux density in the core. The flux is the same everywhere. And this is really because of Gauss's law. But this isn't the best example of the Gauss's law of magnetism. I'm going to give you a few more in a minute. Gauss's law of magnetism would say that the flux is the same in the gap as in the core. That's really what it's saying, but I will give you a better example of this in a moment. So we can then do a bunch of plugging in and everything else, and we can end up with an expression that looks like that, which again, from which we could very easily derive a magnetic circuit. We could also use this expression to find the flux. If we know the physical dimensions and the number of turns of the core and how much current that we're putting in, we can easily find the flux from this expression right here. The magnetic circuit for what we just described would look like this. There's the reluctance of the core, and there's the reluctance of the gap, and this is the flux, and that's the applied MMF. So you can just look at this like a circuit and say, okay, I've got two series resistances, so if I know F is the number of turns times the current, then I can find the flux is n times I divided by RC plus RG. And I would know that RC equals to the length of the core over mu in the core over the area of the core, and the RG is the length of the gap, mu naught in the air, and the area of the gap. We also introduced fringing of gaps. Actually, if you didn't have fringing, the area, these two would be equal if there was no fringing. But the fact that we have fringing increases the area of the gap. So the area of the gap is greater than the area of the core. Usually what we do is we'll state that the area of the gap is some X% greater than the area of the core. Or we could say the area, we have something called a fringe factor or fringing factor. And so what that is we have the gap like this. The flux lines are coming out, they're fringing out like this, making the effective area larger. We might say that the area of the gap equals to a fringe factor, maybe FF, times area of the core, or we might call it a constant sub F fringe factor times the area of the core, where FF or KF is greater than 1. So if no fringing, FF KF equals 1, and the area of the gap equals the area of the core, which physically is not. If the gap was very, very small, the gap length that we're talking about here, that might be possible to make that approximation. And everything we're talking about with magnetic circuits is actually an approximation. So it's okay to come up with these factors, and a lot of them are gained from experience and just rules of thumb. But typically, FF or KF is between 1.02 and 1.06. Those are typical numbers. So that's a you could also say the area of the gap, if the area of the gap is 6% larger than area of the core, then the area of the gap is 1.06 times the area of the core. And so that would be your fringing factor, 1.06. Any questions about that?
I got a quick question.
Yeah.
Does the FF depend strictly on the size of the air gap, or does that also depend on the material?
Great question. It's completely a function of the size of the air gap, really.
Okay.
The strength of the flux has some impact, but it's really, you just have, you got to think of it as more concentrated lines, right? If you have a higher flux, your flux density has gone up. But yes, it's really a function of the length of the gap. You make the gap bigger, you got more fringing. And, yep. Okay, so that was a great question. In this lecture, what we're going to talk about is we're going to show the analogy between Kirchhoff's voltage law and Ampere's law with a few examples, and Kirchhoff's current law and Gauss's law of magnetism. And then there's one more thing I have to teach you before we can go into some examples that will be helpful for the homework. I need to teach you about Faraday's law, electromotive force, and then flux linkage and inductance. So those three things all together. And then I'm going to try to give you some magnetic circuit examples, and if we can stay on track, then we will be talking about AC excitation next time and a little bit about permanent magnet. And then you have everything for the homework. But by the end of today, you'll have enough to do all but the last two problems you probably could figure out, start working on if we get through these examples too. I want to start with...
Excuse me.
Go ahead.
Could you go back to slide 4 quick? I missed part of it, so I was just going to take a screenshot quick.
Okay.
All right, thank you. You can continue.
Sure. Yeah, that's the bad thing, you know. If I was in class, I'd write this on the board and then we could all see it for a while. And that's why I'm recording the lectures. Anyway, here's another magnetic circuit problem. It doesn't always have to look the same. This is a sketch I'd made earlier of really what we're calling a synchronous machine. We're going to talk about synchronous machines later in this class, but this is a synchronous machine that's not moving. It's just fixed with, typically the synchronous machine has a rotating part in the middle here with a winding on it. So it's like a field winding. And then in this case, I'm just showing the rest of it as core material and air. And so this is right here, a core material. It's fixed at a position, but it could move. And then this is the rotor, the rotating part, and then this is the stationary part, also of a magnetic material like a silicon steel or something of that type, and it is it never moves. And what you have is you've got the MMF is applied to the rotating part of the field. You've got an N times I here, and what you will get is flux lines crossing this gap here, and then they're going to split up into, and this is a completely symmetrical structure, so the flux is going to equally split down the two sides. By right-hand rule, it's going in this direction because my thumb is pointing. I'm wrapping, the turns are wrapped around, the current is going in the direction of these turns, so my thumb would show the direction the flux is going to flow around, and then it's going to come back across another gap on the bottom. So there's actually two gaps. And then this is a magnet, really. It's like you have a north and a south pole. So if I've got that same structure where I have this, and I'm making this round like the inside of the stator, which would say that the gap is the same, it's uniform across that. And so that would be the length of the gap. And there's another one here, a length of a gap right there. And then I'm applying the turns, wrapping them all the way around this thing. And there's a current going through it. And then the flux in the middle here, we're going to call this the total flux that we're creating. And then it's dividing up and going through the core. The core area would be just its uniform area everywhere. What I'm really trying to do is I'm trying to keep the flux density of the core the same everywhere. And you'll see why I want to do it this way. So here's the magnetic circuit. First of all, I've got the applied MMF right here, turns times the current. Rotor has a reluctance representing the iron here, and I will divide that reluctance up, R sub R, into two parts just to keep this symmetrical for the moment, above and below the coil. The flux crosses an air gap on the top and on the bottom, so there's an associated reluctance of the gap, and then the flux divides up equally because we assume that we have the same reluctance on the right hand side here of the back iron core as we do on the left hand side, back iron core of the stator. So that's this back iron core here. The flux, total flux supplied by the rotor field winding, this and then it is splitting up into two on both sides. Now you can take this circuit and ask, what is the flux? You could also ask, what is the flux density in the air gap, for example? What is the flux density in the core of the back iron? So to solve the first one, what we would do is we would take our magnetic equivalent circuit and reduce it down by combining up the reluctances. So these reluctances here are all in series. That could be one big reluctance. And these two reluctances here are in parallel. So we've got two parallel reluctances for each side of the stator core. We've got the rotor core reluctance, and then we've got two reluctances for each of the gaps. If we combine that together, we get an equivalent reluctance. And that equivalent reluctance would be the reluctance of the rotor plus 2 times the reluctance of the gap plus the parallel combination of these two, which is, to be completely general, RS times RS over RS plus RS, or this is the expression right here. That would be your equivalent reluctance. And so the answer, the first answer, number 1, is simply the flux is equal to N times I divided by that equivalent reluctance. The second answer is we know that this total flux is crossing the gap. And let's say we have already figured out the gap area. I'm not going to go into the geometrical aspects of that right now. So the flux density in the gap would be the flux going through the gap divided by the area of the gap. And then number 3, the flux density in the core, really on the stator is what we're talking about. But it will be the same everywhere if we assume that, as I showed here, that the area of the core is the back iron core, the stator, and then we say that we've got twice the area of the core on the rotor. And therefore, the flux density of the core everywhere would end up being the flux divided by 2 times the area of the core. I know if the core is unsaturated, so remember we learned about what that is last time. When we learned about the magnetic materials, if we're in this region right here, we're in the unsaturated or linear region. And the relative permeability, the mu r, is proportional to the slope of the line. So really what this is, the slope is mu naught times mu r. But if you compare that slope with the slope right here, where, and this is typically where you design around, that would be the knee of the curve here. It's the mu r of the knee, and let's call this mu r unsaturated. The mu r of the knee is much less than mu r unsaturated. So often we might just assume if we're in the linear region that the mu relative is nearly infinite. And so what does that do for us if we make that assumption? So go back to this example that we just gave here, and let's see how things could be simplified. We know that the reluctance of any core material is equal to the length of the path of the core material, the mu relative times and the area of that core. If mu approaches infinite, or it's very large, in comparison to mu naught would be, say, much smaller than mu, then we could, the reluctance of the core is nearly 0. So we could even neglect it. And so then we went from this very complicated core structure here and we end up with a very, this is approximately zero, approximately 0, and approximately 0. So now we have a much simpler looking magnetic circuit. It's just 2 times Rg, because all of those resistances are now 0. And that's the flux. And so the flux is dominated by the gap. And that is generally the case unless your iron is very saturated. And you could go through, and we could, if we had time, go through a numerical example and prove that to you, if we wanted to do that. Question about that? Okay, well, let's look at another circuit here, and this one is a completely different structure. We actually have 2 different gaps, and the gaps are a different size, and I can draw the magnetic circuit for this. I've got N turns here. So this is N times I. Now it says, in this case, the mu naught approaches infinite everywhere in the core. So I'm just going to, in this case, neglect the core area. And what I end up with is in a circuit that looks like this. 2 paralleled reluctances, the reluctance of the gap in 1 and the reluctance of the gap in 2. In reality, what I had was I had a core resistance here in this leg. I've got a core resistance here. There's a homework problem which is going to require you to not neglect the core resistances, and you have a much more complicated circuit like what I'm drawing. And then you got this area here is bigger than this one, right? So you've got a resistance here, and you're going to have a different resistance here on each side of the gap. These guys could be combined in series. But since they're all 0, I have a much simpler circuit. It's just this. So then, because mu approaches infinite, the flux coming here the total flux. So that's the total flux in this leg here, right where the coil is, would be equal to Ni over the parallel combination of Rg1 and Rg2. Now, what would I do if I wanted to find the flux in this leg, call that Phi1, and on the flux in this leg, Phi2? Well, here what we'll notice is, because we've converted this magnetic structure into a circuit, we have a node here, right? And the current, if we think of it like a current, it's a flux. There's a flux coming in there, and the flux 2 and the flux 1 are dividing up. So what this is really telling me is that flux equals flux 1 plus flux 2, or phi plus phi, phi minus phi1 minus phi2 equals 0. What is that? That is Gauss's law of magnetism, which is the integral of a closed surface of B dot ds is equal to 0. Really says that the sum of the fluxes in a core structure they sum up to 0. And what does that look like? In the electrical world, that looks like KCl. So we have some analogous relationships here. To summarize these relationships, the magnetic circuit, and we have an electrical circuit. So the magnetic circuit has F. It's got reluctances, and it has flux. The electrical circuit has a voltage, resistances, and a current, I, so that's R1, R2, R1. Ampere's law states that the sum, n equal 1 to big N, would be equal to the magnetic field intensity N times the length of the path N, and the sum of those are equal to the MMF. Or we could write it a much easier way and say the sum of the flux in branch N times the reluctance in branch N. This is kind of like a voltage drop, right? It's an MMF drop is equal to the applied MMF F. And that is very much like KVL, which says IN RN equals V. That's KVL. And this is Ampere's law. And if we were to let's add another resistor here. By Gauss's law, if we have this flux here, you could say that's flux 2, this is flux 1, flux 2, flux 3. And by Gauss's law, the sum, n equals 1 to n, of flux n equals 0. And we know that by KCL, Kirchhoff's current law in an electrical circuit, the sum n equals 1 to n of the current n equals 0. Any questions about that? I think you guys can still hear me, hopefully. Let's go back to this for just a moment. This circuit here. if I know the total flux and I know the reluctances in each branch, I can now do current division, right? So I can say that the flux 1 is equal to the total flux times Rg2 over Rg1 plus Rg2. And I could say that the flux in branch 2 is equal to the total flux times Rg1 over the sum of the two, over the sum of the two reluctances, Rg1 and Rg2. So I can apply like flux division, right? Current divider, flux divider. Any questions about that? You guys still awake?
Yep, you're good.
Okay, good. Okay, well, we're going to go to Faraday's law now. This Faraday's law is a bit of a it's a little bit of a challenge to first understand it, but we're going to learn a couple of things from it, and then we're going to be using Faraday's law quite a bit. Now, this is another of Maxwell's equations. It's the third one that we use in this class, and it's the last one that we use in this class. And what Faraday's law is saying is that the electric field intensity, so that's E, and this is bold, but it's really showing that in general it's like a vector. That's the electric field intensity This, of course, you recognize is the flux density. The electric field intensity has the units of volts per meter. Just kind of analogous, right? If you went back, remember the magnetic field intensity was amperes per meter, and the electric field intensity is volts per meter. If you consider the left-hand side of this equation, what it's saying is that the line integral of the electric field intensity around a closed contour that closed contour is, of course, some dimensional thing that's closed. So what does it mean? It's going to be something like this. And what we're going to think about it as a coil, actually. So here is one turn of a coil, and it's closed. We're going to go around the one turn. That's the C. You're going to say it's one turn. It's actually we could have multiple of these, but what I'm showing right here is a turn of a coil. And that's what we consider C to be in a magnetic circuit. If you go to electromagnetics in general, it could be a lot of things. And what we're going to say is that because we're dealing with a magnetic structure, we have coil winding with a very high conductivity, electrical conductivity. And that coil winding, because it is that, we have also a extremely small wire relative to the rest of the structure. Since it is very small, we will neglect, because of these things here, essentially because we have high conductivity, we can have a small wire. Because the wire is small relative to everything else, we can neglect the E field in the wire. And what the result of this, I'm going to give you the result of Faraday's law before we really look at it. We're not going to really look at it rigorously mathematically. But the result of Faraday's law is that this closed contour E dot ds is a voltage E, an induced voltage. So the left-hand side of this circuit here becomes, it's actually a negative E. So we're going to make it equal to negative E here. And what Faraday's law really does is it makes the connection between the electrical world and the magnetic world. Everything to this point, well, we did have current being applied with Ampere's law, but we have to kind of close up that connection with Faraday's law and bring voltage into this picture here. So to continue what we're doing here, we've taken this very general expression for Faraday's law, on the right-hand side of this expression, we have the integral of the flux density that is normally, it's intersecting with a surface at a normal angle. Basically, when I keep saying normal, what I mean is this. Here's your surface. Flux density is hitting this at 90-degree angles here. That way we don't have to do any curls or anything like that. And what we know this to be is the flux. So we have a time derivative of the flux, and on the other side of this equation is a voltage, or an induced voltage. So this induced voltage, as a side note here, E, is something that we're going to call the electromotive force, or EMF. So just like we introduced MMF, now we have introduced EMF. We need to remember this. We're going to keep talking about these two things throughout this class. For this example here, first of all, because I got the negative sign on both sides of the expression here, I can just simplify and say this is E is equal to the time derivative of the flux. Now what I am considering here is that with this expression here, I went around, and this is where I'm not really mathematically rigorous and being kind of artistic about this. I went around the contour, the closed contour, which is a coil, one time. And that's the same as saying I've only got n equals 1, n turns. So I have a turn like this, a coil, and I went around it once. If I go around it more than once, multiple times, and I repeat this process, so this is n equal 1, and then this is n. So in this case I got n, 1, 2, 3, 4, so that's n equal 4. I went around 4 times. What that does to this expression here is it changes for more turns. Every time I do it, I end up with this. And n times the flux. So I multiply the flux by the number of times I went around the contour. And then this term right here is something that we are going to call lambda, and that is flux linkage. So the EMF is really the time derivative of the flux linkage. So this very important equation here that we will use over and over again is the equation for that electromotive force E. That is Faraday's law. Any questions about that? Pretty clear. What's important here, so is really what we've introduced is something called flux linkage. Now, last night I went onto the internet to try to see how the world of the internet, Wikipedia and everybody else would define flux linkage. And this is all I got. Turns times flux. But so what I just went through with Faraday's law is the best I can do to make this mathematically meaningful, and I've taken you through it the way that it is done in the textbook Fitzgerald Kingsley. So this flux linkage, lambda, you take the number of turns times the flux of the core, and we've defined the E, the voltage, as the time derivative of that. Now, one other thing I want to introduce you to is inductance. What is inductance? So this EMF is an induced voltage. And there is, obviously, I don't have a voltage if I don't have a time dependency. So there has to be, in this case, a time dependency of the flux itself in order for us to have a voltage. But there does not have to be a time dependency for us to have a flux linkage. No time dependency is necessary here. What I'm also, another way of thinking about this is the lambda is equal to the integral of E with respect to time. So just going the other direction here. And what I have to think about is that I have a flux first. I have a flux linkage first. The flux linkage may be time dependent, or the flux linkage may not be. It may be time invariant, which you would say, okay, it's DC. There's no AC. This is AC flux, and this is a DC flux. If you take the derivative of a DC quantity or a time invariant quantity, you would get 0, right? So here the d lambda dt equals 0. Here the d lambda dt does not equal 0. So I want to make that clear. The first thing I have is a flux linkage. The flux linkage can also be defined this way: the inductance times the current. So this is extremely important equation for this class. If I had a lambda t that's time dependent, the time dependency could be in the current. As we'll see when we look at electric machines, the time dependency could also be in the inductance, or it could be in both of them. Or neither. There's a static L and a scalar or a DC current. So from this, I can understand and I can find inductance. And I want to do that by an example, and then we'll finish with the examples. Let's see, we almost got, we're going to have to finish our examples next time and then talk about AC. But here's an example right here. Let's take our very simple gapped core. Just showing it two-dimensionally. The area of the core is the same everywhere. I have an area of the gap. I have a length of the gap. And I've got a length of the core. Current going in here, I have number of turns. Number 1, we'll do this all symbolically. Find flux. 2, find the flux density in the gap and the flux density in the core. Number 3, let's find the flux linkage. And number 4, let's find the inductance. So I can go to my magnetic circuit I have reluctance of the core, reluctance of the gap, N times I. This is the flux. So the flux, number 1, is equal to N times I divided by reluctance of the core plus reluctance of the gap. The number 2, the BG is equal to the flux divided by the gap area, and the flux density of the core is the flux divided by the core area. I've got 1 minute, and this doggone surface is freaking out on me. All right. Just a minute. Okay. So let's find number 3. The lambda is simply N times flux. And that is equal to N times I over reluctance of the core plus reluctance of the gap, or N squared divided by I, or N squared times I divided by the total reluctance. That's the lambda in this case. And now all I have to do is find the flux. Now all I have to do is find the inductance. So we learned that the lambda is N times the flux, but the lambda is also equal to L times the I. So the L is equal to the flux linkage divided by the current. So in this case, I would just divide the current out of that flux linkage expression, and I have the inductance, N squared over the total reluctance. And that's the inductance of that coil and core structure. So basically, this is an inductor with a coil and a core. And I've been able to find the inductance using my magnetic circuit. Do you have any final questions about this? You guys are really quiet.
Pretty straightforward.
Yep. It's pretty straightforward so far. the homework that you're doing is going to practice this with all kinds of different core structures and core and coil structures. So we'll pick up some examples. We'll talk about multiple coils next time. And we will talk about AC excitation. Right now, what I've looked at here is really a scalar example, or it could also be a DC coil. So you have a DC inductor. We could look at what we just did right now as a DC current into an inductor having an inductance. And okay, any other questions? Everybody's been really quiet today. And okay, I hope you all have a good weekend, and we will see you again on Tuesday. I will post information about when our final is. Once I know where we'll do it, I will let you know. And I'll stay online if anybody wants to ask me anything. And again, feel free to contact me individually if you need to meet with me or ask for specific help.
Thanks, Professor. Have a good weekend.
Yep. Thank you, George.
Would you mind going back to the slide where you laid out the magnetic circuit and the electric circuit?
Sure. Right here.
Yeah, that one.
Yeah.
Thank you.
Yep.